In this lecture series we're going to be talking about diodes. This is a basic introduction to diodes in the context of a first circuits or electronics course that might be taken the sophomore year of an engineering program, undergraduate engineering program. So we're not going to really talk about the semiconductor physics of diodes. We're just going to look at how does the diode behave at its terminal characteristics, the current, the voltage relationship, etc. So we're going to split this up over several lectures, and we are going to begin by talking about the ideal diode. Then we'll describe the Shockley diode, which is an exponential relationship or equation that describes the underlying physics of a diode. And then we'll look at some variations or differences, discrepancies between the Shockley diode and a real diode. And then we will develop, fourthly, some simple diode models that we will use then when analyzing diode circuits. Fifth, we'll develop the small signal diode model. So when you look at incremental changes in voltages or current associated with the diode, you can replace it with a small signal resistance and thereby linearize it. And then sixth, we'll analyze some diode circuits making use of both the small signal and our diode models. Okay, so let's begin with the ideal diode. All right, the diode has a symbol like so. I'm going to label the voltages V, D, I, D, and notice that's the passive sign convention. The current goes into the positive terminal, and as the symbol might indicate, you can think of the diode as conducting current only in one direction. Diode is analogous to a water check valve. Okay, so if any of you ever had a well at your home, you might have seen that on the, if it was a shallow well and the motor was sitting, like in our house we had a shallow well, and the pump was in the basement, and there was a holding tank, one of those blue tanks that the motor sat on, and the inlet pipe went through the foundation wall and then went down maybe 15 feet or so to where the wellhead was. And on that motor in the basement there was a check valve. So the idea was that once you filled the pipe from the wellhead with water, you don't want to lose the water that's in there once you turn off the motor. So whatever water you pull up, you want it to stay in the column and not be able to flow backwards. And so there is a check valve, which essentially, if you have a pipe like so, a check valve might be inside here. You would have a flapper. So I really can't draw it very well. Let me draw it in a 2D. But the idea is that maybe you would have, that's like a ring that would block. Let me redraw this way. Water could flow like so. Maybe there was a hinge, so this thing could swing out and allow water to flow through. But if the water tried to come back in the opposite direction, okay, the valve would shut and there would be no water flowing back. Okay, so it's like a flapper. We have valves like that in our heart, right? So that's the analogy. The electrons, or actually charge, we'll talk about positive charge, can only flow this way, and similarly what's actually flowing in our circuits are actually electrons. So electrons can flow to the left but cannot flow to the right. So we can model our diode initially as a simple switch. Okay, so the diode, I thought I'd change my color. The diode can be thought of as being in one of two modes. Alright, it will either be an open switch or a shorted switch. So the switch will be open if the voltage VD is less than 0. Okay, and the switch will be closed if the current ID is greater than 0. And so when we solve circuits with this ideal model, we will replace the diode with either an open circuit or a short circuit. And of course the trick is that you need to choose the right one. And we use the technique of solution by assumed state. So you just assume one state, solve the problem, and then determine whether or not the conditions for that assumed state are valid. So for instance, if you assume that the diode is open, you would you'd replace the diode with an open circuit, and then you'd have to make sure after you solve the circuit that that the voltage across the diode was actually less than 0. Okay, so we'll come back and do some problems using the ideal model later. Let me draw the IV characteristic for the ideal diode. Okay, here's VD on the horizontal and ID on the vertical, and the curve that we'll have is that we said it'll be a short if the current is greater than 0, and it will be an open, meaning there's no current, right? This means I is equal to 0, and this means V is equal to 0. Maybe I should do these in two different colors. That might be useful. So let me redraw this, and we'll do this in orange for ID is equal to 0 here. Okay, and in this range we have VD is less than 0, and in this range here we have ID is greater than 0. All right, so that's our ideal diode. Now let's move on and look at what an actual diode curve looks like. So the Shockley diode. By the way, when we depict an ideal diode, I'm going to try to remember to put a diode with an I inside it or next to it. Okay, I for ideal. When we solve a circuit having a diode and we want to treat the diode as a Shockley diode, we'll put an S in it or near it if we don't outright specify it in the problem. Okay, so here's our current. Turns out that the way that the IV characteristic looks for a non-ideal diode, it is an ideal Shockley diode, I guess, is as follows. It's an exponential curve, okay, and it goes down just ever so slightly. This is exaggerated, so this is not to scale. Okay, this right here is IS, and it's constant in this whole region, the negative region. Basically it stays at IS. Okay, and here's the Shockley equation. The current in the diode is equal to this scaling current IS times E to the diode voltage over N times VT, that whole exponential minus 1. Now we're going to find that we can simplify this expression a little bit by basically defining two different regions of operation. When the diode is working in the, I guess it's the third quadrant, down in this region down here, okay, it turns out that we can approximate the diode current as simply minus IS, and that's because for VD less than 0, the exponential becomes much smaller than the minus 1 that is added to it. And similarly, when the diode is actually conducting over here in the first quadrant, we'll be able to approximate the diode VI relationship as IS e to the VD over N VT and drop the -1. And the reason for that is, IS is typically in the range of 10 to the -9, maybe to 10 to the -12 or more. Okay, so it's very small. And if we're typically in our type of applications that we'd look at in a class like this, the currents we're interested in when the diode is conducting is on the order of milliamps, tens of milliamps, maybe 1 milliamp, maybe 100 milliamps. So clearly to conduct, the exponent term has to be several hundred, well, not more than several hundred. If it's going to offset 10 to the -9, it's got to be at least 10 to the 6th, right, in order to produce a milliamp. Okay, so let's talk about some of the parameters associated with the diode parameters. So what we have is this IS, which is the scaling current, or saturation current, it's called also, saturation current. And we also have N, which is called the emissivity or ideality constant, and it ranges typically between 1 to 2, so it can go outside of that. And when we have discrete diodes, so a discrete diode is a diode you can actually pick up in your hand and it has 2 leads on it. Typically the value is around 2, and when the diode is part of an integrated circuit, then it is closer to 1. Okay, that's related to the physics and the properties of the semiconductors and the fabrication. So when it's actually inside of, say, an integrated circuit like a microprocessor or an op-amp or a driver circuit, whatever, then N is closer to 1, but that's the range of it. Now we also have VT that showed up. This is actually not a parameter of the diode, but actually a parameter of the environment. It is KT over Q, where K is, or Q is, the charge of an electron, and K is Boltzmann's constant, and T is the junction temperature, junction temp. And so really the junction temperature is the only one that we can that will actually change. But here's a typical value, 25.2 millivolts at, I think, 20 degrees C. So we often use 25 millivolts, or 1/40th of a volt, for room temperature problems. So really there are 2 parameters here that describe the diode, and those are IS and N. Okay, so these describe the diode, just like the resistance R describes a resistor. Here we have 2 parameters. Okay. Now let's manipulate this equation that we have a little bit to find some, just to get familiar with it. So we're going to assume diode is conducting, which means that we can then use our approximated equation right here. ID is approximately, and I'll probably just say equal after this, Is e to the Vd over n Vt. If we take the log of both sides, then we'd have on the right log of Is plus log of our exponential, which of course just gives us Vd over nVt. And if we bring this guy over to this side, we would have log Id minus log Is is equal to, and we can put that whole thing times nVt is equal to Vd. And let's clean this up. Okay, so therefore we can write Vd, the diode voltage, is equal to nVt times, and I'm going to combine the difference of these logs. It's going to be log of Id, log of the quantity Id over Is. Okay, so here's another version. Okay, this is equivalent, right? But it is expressing the diode voltage instead of current, in terms of current rather than the current in terms of voltage. Now the interesting thing is we can actually, let me in fact rewrite this as by splitting up the log here. Okay, we'll have this term here. Okay, now let's say here, I'll just say let L equal the log of ID, okay, or we'll say X. Let X equal the log of ID. Then we'll have V diode is equal to nVt times X minus nVt ln Is, which is really this form of an M times X minus or plus B. Okay, where B is equal to minus nVt log of Is, and M is equal to nVt. Alright, so let's plot this. If we plot X, which is really equal to the log of ID, we find that we have a straight line. The slope is nVt, and the intercept is going to be minus, so this point here is going to be minus nVt log of Is. And what else can we say? Okay, and the vertical here is Vd. Alright, so now I can equivalently plot this one more time, but instead of writing X for the independent variable, I'm going to go ahead and write ID, but I'm going to actually draw a logarithmic scale. Okay, so if we said something like this was 1 microamp, 10 microamp, 100 microamp, 1 milliamp, 10 milliamp, 100 milliamp, okay, then we would also have a straight line, and the slope would be nVt. Alright, let me show you a real diode curve. This is a diode curve for a 1N4148 diode. It's a very common diode that we use a lot in basic circuits courses. It's a signal diode. meaning that it is not a power diode. It's not going to be found in a big power supply, but when you're processing signals, so it can handle up to tens of milliamps. Here's what a diode, that 1N4148 diode, looks like, and the it would be oriented like this. Okay, so the black band on the diode actually indicates this crossbar here, so it's plus to minus VD, and current is going to flow this way. Just FYI, here are a couple other diodes. So this black package here it doesn't have a black band, but it has a gray band, right? And that indicates basically the diode points that way. Okay, so this vertical bar corresponds to that right there. Evidently this guy is oriented the other way. Okay, so what we have here is a curve that shows the forward voltage, VF, okay, or what is equal to what we're calling VD. Okay, sometimes they call it VF, sometimes they call it VD, and this current here is ID, or they'll call it IF sometimes, forward current. Okay, and the question is, let's find N and IS for the 1N4148. Okay, using what we've found before, what we've just discovered. The slope here is going to be NVT, and that's because if you notice, the horizontal axis is a log scale. So we got 0.1, and then 1, and then 10. All right. Notice that the data is taken at 25 degrees. So we're going to assume that VT then is going to be equal to, we'll just approximate it, 25 millivolts, but it's actually going to be a little bit higher than that because it's 25 millivolts at 20, but it's good enough for our purposes. Okay, so what is the slope? We're going to have a rise. We'll say that NVT is going to be equal to delta, a change in voltage of, let's see, from 500 up to about 735 or so. 735. Okay, so delta voltage equal to 735 millivolts minus 500 millivolts. Okay, divided by a change in log current. So we'll have the log of 0.1 milli minus the log of 10 milli. We can rewrite that as 235 or 0.235 volts divided by the log, natural log of 0.1. Actually, I've got this backwards. I'm sorry. This should be 10 milli. This should be 0.1 milli. So we'll have the natural log of 10 milli over 0.1, which is 100. Right, 0.235 volts over the natural log of 100. And then we can also, you can just evaluate that, or the other way to do this is you can write this as the log of E times the log of 100, and that is 0.235 over log of E is about 2.3. Log of 100, base 10, is 2. Okay, and we're actually solving for n, right? That's what we want to find out. So this is going to be n equal to, remember VT is equal to about 1/40th of a volt. So we're going to multiply by 40 times 0.235 over 2.3 times 2, and if you crank that out, it turns out that it's 2.04. So n is equal to 2.04, which is what we would expect for a discrete diode. Actually, it's a pretty ideal there. Okay, so that's how you would find an n from some data. Now this curve I got is straight out of a data sheet. All right, this is from 1N4148 data sheet. So you can just Google that and find that data sheet and calculate n, and then the next thing is to find IS. So if we know that ID, what we'll do there to find IS, so find IS, let me change to a different color. Find IS, we're going to pick just one point. We have, we might as well pick the at VD equal to 500 millivolts. I'm picking the bottom point there. We have ID is equal to 0.1 milliamps. Okay, so we have ID equal to IS e to the VD over NVT, and we could equally write IS is equal to ID times e to the minus VD NVT. So we just plug that in. We've got 0.1 milliamps, e to the minus 0.5 volts, divided by 2.04 times 25 millivolts. And if you crank that, you'll find that it's 4.9 nanoamps. Okay, 10 to the minus 9 amps. Okay, so therefore, the 1N4148, by the way, many diodes begin, or at least older diodes that have been around a while, begin with 1N. Okay, and you'll find that a number of transistors, bipolar transistors, start with 2N. Okay, therefore this can be modeled as a Shockley diode with N equal 2.04 and IS equal to 4.9 nanoamps. Now there's a little bit more to this model, or to this diode. Notice that this particular curve that I provided was for currents between 0.1 and 10 milliamps, but this diode is rated above 10 milliamps. So here is the curve from the data sheet for the 1N4148, but over a range of current that extends up to 800 milliamps. So we just looked at the region down here. Okay, previous graph was right here, and what we find is that this curve, doesn't remain a straight line. Okay, it actually starts curving up. And what that tells us is that the Shockley equation does not adequately capture the DC VI characteristic of this diode. At higher currents, the voltage actually grows across the diode faster than the Shockley equation predicts. And it turns out if we were to plot this now on a linear scale, so linear voltage versus linear current, you'd actually see that in this higher current region you would start to see a VI curve that was actually linear in the linear domain. In other words, it starts looking like a resistance. And so what's going on in this region here is due to ohmic resistance. So the Shockley equation does not predict or doesn't include any ohmic resistance in the semiconductor material. It's just based on the physics of the semiconductor junction that makes up the diode. But any semiconductor material is going to have resistance to it, and so that has to be represented by an additional resistance. So we need to augment. We need to augment our model. So let me go back to the outline here initially. We were going to talk about the ideal diode, the Shockley diode, and then the real diode. And we've actually been talking about the real diode here. So let me put in number 3. Okay, real diode. Okay, and at this point, to take a step closer to modeling a real diode, we need to augment our model. This is still, there's a lot more that can be said about diode models. We're only looking at small signal, signal diodes. You get into power diodes, and there are people who spend their whole careers modeling diodes, and so there's a lot more to be said about this, but we're going to stop at this point. This is as complicated of a model as we will have. So we'll start with the Shockley diode model, and we'll just add a resistance RS, or RD, sometimes we call it, I guess, RD, RS. Okay, this voltage here I'm going to call VS, or maybe I'll do this. VD. We'll call the overall current IF, and the overall voltage of our device VF. Okay, put it down here, and clean this up. Okay, so we'll have VF, the overall voltage of our diode. Okay, so if I draw a box around here, this is our diode model now. Okay, so we'll say that VF is equal to V of the diode, the Shockley diode, plus RS times the current, where VD is equal to IS e to the VD over I'm sorry, that's not right. Where VD is going to be equal to NVT log of IF, the current flowing through it, divided by IS. Okay? So we're going to use two devices, if you will, to model our diode. The Shockley diode, described by the Shockley equation, and then just a regular old resistance to capture this deviation up at higher current. So let's estimate RS. How do we do that? So what we do is we go out to, say, the 800 milliamps here, and we're going to estimate what the delta V is here. All right, and that turns out to be roughly 0.4 volts, 400 millivolts. Alright, so we see that by at 800 milliamps there is an added 400 millivolts across our diode that the Shockley diode does not account for. Okay, the Shockley diode would account for about 1.05 volts right here, 1.05 out of 800 milliamps. But we have an additional 400. So therefore, we can estimate RS as being approximately 400 millivolts divided by the 800 milliamps that are flowing. So that is about 1/2 of an ohm, 0.5 ohms. Okay, so now our final 1N4148 model is, we'll have a Shockley diode with the resistance. We'll put 0.5 ohms there. We'll say N equal to 2.04 and IS is equal to, what was it, 4.9 nanoamps. And that is our diode model, IF and VF. To complete this video, I want to now show you a simulation using the model that we just created. So I've pasted in the little netlist or circuit deck that we're going to simulate, and we're going to use ngSpice because it's available online. There's an online version here at ngspice.com. I've entered in the netlist as you see right here. It's simple. I'm going to basically, here's the circuit that I'm actually going to simulate. A current source, I1, going from node 0 to node 1, and then the diode going from node 1 to 0. Okay, and we're going to program the current to go from 0.001 amps to I think 0.1 amps. Okay, it's going to be a DC sweep. So I have .DC. We're going to sweep the 1 amp source from, I guess, 10 microamps up to 1 amp in increments of 0.1 milliamps. Okay, so at every value it's going to do a static solution, solve the equation, then save the results, primarily the voltage across the diode, and then we'll put all those together. So let's, and then here's how you specify the diode. You call it out when you use it by some name that you make up. So I called it my 1N4148. And then this statement here is where you specify your model. You start out with the dot model, and then you give your diode name. The letter D tells Spice that this is a diode model, and then afterwards you put the various parameters that you want to specify. Spice knows about the Shockley equation. In fact, there are a lot of other parameters beyond this that you can specify, but they kind of all take default values or zero values unless you specify them. So we're specifying N, IS, and RS. So let's simulate this, and then I'm going to plot V1, which is the voltage across the diode, and I want to put it on a log scale, X log scale. So here it is. Hold a second, I'll zoom this. Okay, here we go. So we're plotting the voltage versus I sweep right here, going from 10 to the minus 5 to 1 amp. So we can compare this to the data sheet, which is going from 10 milliamps in this case, but the one previously started out at 0.1 milliamps and goes up to 800 milliamps. So almost as high. 800 milliamps is just around right here. And you notice that we have the same trajectory. Let's check at a point here. We find that it crosses 0.8 volts just above 10 milliamps. So if we go back to our model, here it crosses 0.8 amps at above 10 milliamps, basically at 30, partway between 10 and 100. So it crosses 10 milliamps, crosses 0.8 volts between 10 milliamps and 100. It's perhaps a little bit off. We could tweak this again to get a better fit, but it should fit pretty well. So we'll stop here, and in the next video we'll continue on with these 4 topics.